there's two lessons. One, just transformations of a radical graph, right? Moving a radical graph around. The second one is this one, where I take linear and quadratic functions, or any function technically, but most of the time it's linear and quadratic, and I put the entire function under a radical and see what happens. Okay? So here it says, to graph y equals square root f of x, you can set up a table of values for the graph of y equals f of x. Then take the square root of the elements in the range while keeping the elements in the domain. What the heck does that mean? Well, that means that I need to pick the marker first. So that means if I look at this graph below, I have x, I have f of x, and I have square root f of x, let's say. Okay? So off of this original graph, I have negative 0 and 0.5. It's this linear graph. So the graph, the original graph is this f of x graph, and this is just the square root of f of x. You see that? So I'm just showing you what we did here. This is like an example. So on this graph here, let's say I take negative 2 and negative 3 as one of my coordinates. So I have negative 2 and negative 3. Then I also have negative 0.5 and 0. Then I have 0 and 1. Then I have 4 and 3. And 8 and 4. So those are the ones on f of x, on that line, correct? I'm just taking the points off the line, yes? Sure. So if we have y equals f of x, and now we have, what's f of x in grade 10? What did they tell you to make you feel a little better about yourself? F of x is just what? Y. Don't freak out. Okay? It really is just y, but it's a specific y that goes with a specific graph, though, correct? So we use f of x and g of x and h of x when we have more than one graph on a Cartesian plane, so you can tell the difference between them, right? That's why you start getting introduced to f of x's and g of x's and h of x's. Because if I just go y equals y equals y equals, which equation is that, right? So if I have y equals f of x, and then I tell you the next one is y equals square root f of x, what am I literally doing? I'm taking the y's of this function, because f of x is just y. That's all it is. Don't worry. It's just y. Everyone calm. That's what we do in grade 10. You're freaking out. It's just y. You'll be okay. Okay? So we're taking the y's and we're doing what to them? We're rooting them. Are we doing anything to the x's? No. So our x is staying the same. We're literally just rooting our y's. That is all we're doing. That's all this lesson is. This lesson is keep your x, root your y, redraw graph. Keep your x, root your y, redraw graph. That's it. That's all it is. It is the concept that you have to take home in order to be successful in this lesson. So, what did we do? Okay, we went negative 2 or negative root 3. Well, my new y is going to be negative, is the square root of negative root 3. Can I take a square root of a negative? No. So this whole entire part of the graph, which I'm going to change to a different color, doesn't exist on the root graph, does it? It went away, didn't it? So where's the first point that's we're going to start at every single time?
0.
When y equals 0, right? When y equals 0. So our x-intercepts are extremely important. We have to find our x-intercepts every single time on every single equation, because that is going to be where our domain is going to start. That is going to be where our graph is going to start. It's always the x-intercepts. So this one here is negative 0.5 and 0, while root 0 is still 0, right? It stayed the same. Do we agree? So this stayed the same. What happens when points stay the same and do not change? What are they called? Invariant. So that's one of our invariant points, right? What other y will become invariant? What other y, when I take the square root of it, stays the same? 1. So on this 2.2 lesson, whenever I take the square root of a full function, when y equals 0 and y equals 1 is where I'm going to find my invariance. And sometimes that's the only question they ask you. Sometimes they'll say, what are the invariant points between y equals f of x and y equals square root f of x? And it's just when y equals 0 and y equals 1. So we go root 1, which is 1, which is still invariant, so it stays the same. So when I go to sketch a square root graph, I literally just go to these 2 points and I immediately make them the same. Now what happens when I take a square root of a decimal between 0 and 1? So like say the y is 0.5. Take the square root of 0.5. Everyone do that. Because when I take the square root of 4, it's 2. Take the square root of 9 is 3. It gets smaller, right? But if I take the square root of a number between 0 and 1, so 0.5. gets bigger. What about 0.25? Square root of 0.25? It gets bigger, right? Actually, when you square root a decimal between 0 and 1, the number actually gets bigger. It's the only place where your y value gets bigger when you square root it. Anything greater than 1 is going to get smaller, right? So I always also go to my 0.5, and I draw it up a little bit at 0.7. Do you see how they did that? So it's actually curving like this. Do you see how the curve's happening? Then we get root 3. 4 and root 3, I think root 3 is 1.73, blah, blah, blah. And we get that from the tan and the cos of 30s and 60s, right? So we go 4 and then 1.7 something. What? 4? Oh, 4 is not 3. 4 is what?
4.
9. Wow, that's way easier than what I wrote here. I didn't write the original. Here. 4 is 9. So it's the root 9, which is actually 3. So our new point's 4 and 3. That's way nicer than what I think. Okay, let's work our way backwards. So I wrote 8 and 4. 8 and 4 is actually a radical graph, right? What was it on the original? 16. Sometimes they'll give you the radical graph and ask for the original, right? So you'll square back to get the original. You square root to get the radical. So this one would have actually been 8 and 16. So it would have been like up there, right? Just doesn't exist because our graph is not there. So we can go from a radical graph to an original and original to a radical. Does that make sense? So where did this graph actually go? Well, this original domain was XER, YER, because it was a linear graph, correct? But our domain of this one is actually going to be x is greater than negative 0.5. So the x-intercept is extremely important to get your domain. If you don't have the x-intercept, you won't have where the graph exists. Now the range is y is greater than or equal to 0. And most often the range will be y is greater than or equal to 0. Because if I have something like this, right, as my original, my radical is actually going to do this. These will be invariant. This will pop a little bit up. This will go like this. This will go like this. Yes? And my range is still greater than 0 because the bottom goes away. You can't take square roots of negative numbers. Where is the case, though, that it won't be greater than or equal to 0? What type of graph has to exist in order for the range not to be greater than or equal to 0? Anyone have any ideas?
If you have a graph that doesn't have an x-intercept.
Exactly. So what about a quadratic that has no x-intercepts, no solutions, right? So we could look at like y equals x squared plus 4, let's say. So if we looked at y equals x squared plus 4, that is a vertex at 0, 4, and a y-intercept at 4. So it's literally here. And it's going like this. So where is this point going to move to? 0, 4 is now going to be 0, 2. And then it'll like arrow out. It'll get just wider because these will get flatter, right? So what's my range actually? Greater than or equal to 2, not 0. So as long as they have x-intercepts, your range will always be greater than or equal to 0. If there aren't x-intercepts, that's where you're going to run into problems where you actually have to find the minimum and then take the root of that. Okay? Sometimes they'll also just give you functions and then ask for it. So they'll give you like a function like this. They can do whatever they want. They can go and then ask you to draw that. Or they can give you something like this. And then ask for the square root of that, right? So you really just need to know the rule of what's your mapping. Well, let's talk about our mapping. Our mapping for all of these are xy. Nope. xy becomes x what? Square root of y. That's it. That's all the mapping is. Remember the mapping for inverse was xy becomes what? yx. This is just xy becomes x root y. Your x's stay the same, your y's get rooted. Okay? If we can remember that, I can give you any function. It doesn't matter what it is, and you can find the square root of it. We agree? All right. Here it gives you a little summary. If f of x is less than 0, it's undefined because you cannot take the square root of a negative number. If it's equal to 0, that's where it intersects. These would be invariant, invariant. The graph of y equals f of x above and then below. So we're going to flip over to here. So whenever you have to take the square root of a function, what's the very first thing you're going to have to do? Perhaps graph the function. So go graph the original function. And what is the most important parts to find? Points to find, not parts.
Yeah.
Points. The x-intercepts also, where's the other place where invariants sit? 0 and 1. So you need to find the spots where y equals 0, y equals 1, and then other coordinates as well. So sketch the original. On the separate sheet of paper in front of your face, we're going to discuss something. So the curriculum comes out, well, the curriculum for this curriculum came out in 2012. Grade 10 in 2010, grade 11 in 2011, grade 12 in 2012. So easy to remember, right? Yes. So it's been out for quite a tick. So what they do at the end of the diploma is they give us out this this paper, and this paper, the sheet. And the sheet tells us this is where the kids are doing well, and this is where the kids need help. Okay? Now sometimes it shifts because what happens, teachers read, oh, this is where they need help. And then we like really focus on that, so then they get better at it. And then the good things start sliding because you focus on good things. Sometimes the bad things never get better. This is one of them. This one is on the sheet every single year. It's determining the invariant points between f of x and square root f of x algebraically. Okay? It's where people are not the best. So we're going to do, that's why I gave you the separate sheet. It's actually quite a bit of work. So we have the graph of x squared plus x minus 5. Now I could use this function, or I could use the square root of it and find the invariant points algebraically, and it wouldn't matter because their invariant means they stay the same, right? So you could use the first equation or the radical equation, and they're going to remain the same. Well, I'm not going to use the radical if I have a choice because that's just more work, correct? So if ever you're told to find the invariant points algebraically, between we just need to remember where the invariant points happen. Where the invariant points happen. Yeah.
Y equals 0, y equals 1.
When y equals 0 and when y equals 1. Wait a second. When we did x equals 0 and x equals 1, we just solved it. We plugged it in, we got the missing variable, correct? That's what we did when we were finding x-intercept and y-intercept. It's the exact same thing. Usually, one factors nicely. Usually, the other one has to be put in quadratic formula to get exact values. That's the catch. That's it. This is not a hard concept. It is done terribly. Yeah, on the diploma. Most people don't answer it. If it's in a written response, it's not answered. So, all we do is we take either the original or the square root function, set the y is equal to 0 and 1, and solve for them. That's it. So, I know this graph is below the x-axis, so I know I'm going to get two x-intercepts in two places where y equals 1, correct? So I should get two solutions for y equals 0, and I should get two solutions for y equals 1. So let's try it out. So we're going to go 0 equals x squared plus x minus 5. Can that factor? No, it can't factor. What do I have to immediately do? Quadratic formula. Can root 21 reduce? If your root can reduce, must you reduce it? Yeah, not an option to not reduce. Okay? So, is that a point? Is that a coordinate? No, so sadly, some people will get to this point and they'll actually get values for x, which is amazing, but then they don't write it as points, and then they lose marks again because it wants the invariant points, right? So what are my invariant points for this one? My 1 is -1 plus root 21 over 2 is my x. What's my y? And then -1 minus root 21 over 2 and 0. Now I just repeat, but my y is 1. And this one factor? No, these are both evil. They're both decimal.
Why are you adding one?
I don't know. Oh, it is nice. Ignore me. Check that. I was just seeing if you were paying attention. The ultimate teacher comment. And you were. Good job. AKA, I made a mistake. So I'm covering it up. Oh. Oh, look at how nice that is. What do I get?
Numbers.
When they are? And? So people will often leave it like that. Is that good? That's some really nice x values, still not invariant points. So what's my point?
3. Wait, -3.
Yeah. Okay, we're going to go back to our graph. Do you want to know what else is a sore point in my life? Marking your graphs. That is a sore point in my life. Because you're really good at so many things. Okay? Start with that. Positive reinforcement. Graphing isn't always one of those things. You know, because you guys get a few points and then you like sketch from your eyesight or something, which is never a good thing. We do not want to sketch from our eyesight. We want to sketch from accuracy. So, let's go down here. Our 1 point for y was what? -3 and 1 and 2 and 1, I think. I'm sketching the original. My x-intercepts were at what for decimals? Because I need to have them as a decimal to sketch them. So find them. Type it in, find your x-intercepts. You can either type it in this way or you can type in your answers, right? We just found the x-intercepts. -2.79. Positive can't be that. What would the positive be? 1.79? Okay. Now that's not enough points for all you 4-point people. We need a whole bunch of points, correct? Okay. So I'm going to go second table. It's an amazing thing. You should try it out. Actually, I need to find what first? Starts with an M, rhymes with minimum. The minimum. That was scary. Rhymes with minimum? You just popped in. I'll say that that's the reason why. Okay. So I know people will be like, but the minimum goes away, it doesn't matter. Yeah, it does. If they want you to draw both accurately, it certainly does. You can't be like, it looks like it's about, there. Perfect. You're like, I'd never do it. You do. You guys do. You do. You're like, looks around. There. Yeah. Yeah. Right about there. So sad. Yeah. True. They won't mark it that way, but yeah. So I got myself -0.5 and -0.525. And when it's a weird decimal like that, I'm like, hey guys, I'm so smart. I just found it. You're welcome. And then I write it all out for you. I'm like -0.5, -5.25. Oh, I know. So 5 points, that's enough, right? No, it's not. You have a calculator, it has so many points. So I'm going to keep going. All right, I got myself a 0 and a -5. Thank you. I got myself a -1 and a -5. Good, good, good. Cool, cool. I have a -2 and -3. I have a 1 and a -3. I have a 2 and a 1. I have a 3 and a 7. I have a -4 and a 7. Could I get more points in between? Can I? Let's try. Second trace value. I want to see what's at 1.5. Oh, -1.25. Cool. I'm curious as what's between 2 and 3. Second trace value, 2.5, 3.75. What's between 3 and 4? Second trace value, 3.5, 10.75. Oh, that still fits too. Look at how much better my graph is getting. So many points, so little time. Except you have a test that's supposed to be done in 2.5 hours and they give you 6. So if your graphs suck, I'm just sad. The diploma is set to be done in 2.5 and they give you 6 and you give garbage graphs. I'm just like, girl, please. That's what I'm thinking in my head when I'm marking them. I'm like, you had so much time and you had such an expensive calculator. You might as well get your money's worth, right? Okay. Now, please connect between the coordinates. It's a lot harder for me to do it. Okay. Perfect. Then what do? I type in the square root, and then I just go like this. Perfect. Take a look, see at yours. It might look somewhat similar. Okay? Not cool. I'm going to take those off. I hope it doesn't take more graph off. Okay. So what do? We immediately go to our graph and we go, okay, this one's going to stay the same. 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 They're invariant. We agree? My 0.5 is going to go what? Higher. I wish you guys had Saskatchewan and Telemiracle. You don't even know what I'm talking about. But it's like, where are we going? And they go, hi. Where are we going? And they go, hi. But you're in Alberta and you don't understand. It's so disappointing. Google Telemiracle at some point. And it was like the best week of our lives. Okay, and maybe it was a weekend. I can't even remember. It's so long. So, 0.7, 0.7. It was for raising money. It was work small. Love it. Okay. Where else do I want to go? See? Higher. That's what I really want to answer every time. It's embedded in my soul from a child. We only had like 2 channels, and when Telemiracle was on, we literally just had Telemiracle. So if your friends would go and like sing on it and stuff, and then they raise money, and then they go, ring those phones, which I don't even know if they ring phones anymore. It's probably like, go on the internet, go on the internet. Yeah. I have to check it out. I haven't checked out Telemiracle forever. You guys are missing out being in Alberta. All right. Square root of 7 is 2.6 something. So that would drop down to here. And then this one would drop down to 2.6 something. Could I use more along the way if I wanted to? Yeah. If not, all I can do is this. Do you see how I put an arrow at the end here and I stopped? Why can't I keep going? Any point after that is sheer guessing. That's what that is. Right? You have no y's that you're taking the square root of after that, are you? So could you go onto your calculator and get more y's and square root those? Because I know that these will drop down, right? So I could keep going and they would drop down, and then I can accurately graph. Sure. Off of what I have currently, anything after that is a sheer guess. You're just extending lines at that point, and you're making your graph less accurate, not more. Okay? So what is my range for this one? And I mean the y equals f of root f of x graph. What's the range?
0.
Or
Y such that y is greater than or equal to 0.
Yep. What's my domain? Nope. Let me write down my little numbies. -1. Can we use rounded decimals? No. This one here is -1 minus root 21 over 2. This one here, oh, and 0, sorry. We agree? So my graph is less than that beautiful rational number and then greater than it. So I would say in interval notation, you'd go negative infinity union
Only half of us know what that is.
the union. This means or. The U just means or, because you can either have x values that are less than this, or x values that are greater than that. The U just means or. And if it was this way, it would mean and. Well, there are no x values that are less than this and greater than that. There's not an x value in the world that would suffice that. So that's why you have to use the union, because it means or. Sure. In set notation, it looks like this. Y is less than, why am I using y's? Oh gosh. I literally, there we go.
Question does say why. Which one?
It's a struggle. X such that x is less than or equal to -1 minus root 2 over 2. And then we say or. Okay? Then we're moving on. Flipping over. Easy graphs, don't do that. A little bright sun that moves through the crack of that window and blinds me. Okay. Oh, sorry, I want to do this one first. Example 3. So here it says, for each point on the graph, write its corresponding point on the graph of y equals root f of x. All we do is what? Keep the x, root the y. It's mapping, right? So this one is 3, 0. It's going to actually become 3, 0 because it's invariant. What about -5, 25? What about 9 and 15? 9 and root 15, which you can't reduce. Done. What about this one?
No.
Yeah, so it becomes 4, just no. 16. So the coordinate does not exist. Then I want to flip over again. And I want you to pick the matching graph. So it's example 5. They're a little wonky. I scanned them and they went crooked. Couldn't hold the page straight. You'll be fine. Pretend they're straight. I believe in you. So these are the originals. These are the options of its rooted. Okay, match. Go. Pretend these are not crooked. I believe that you can. I don't even know why there's this black line that's in there either. It just does what it is. Yeah.
We still.
Right. So, yeah, your lowercase letters match up with a capital letter below it.
Sitting down doing nothing. That's fine.
Okay, so I just want to go through the answer to this one. So, what's going to happen here? This is going to stay invariant. This is going to stay invariant. 0.5 is going to move up to 0.7. 4 is going to drop down to 2. 9 is going to drop down to 3. You're going to get something like that, which matches which one? C. This one. This remains invariant, this remains invariant, this remains invariant, this remains invariant, this moves up to 0.7, 0.7, 4 drops down to 2, 4 drops down to 2. It's going to go something like that, which is A. That's your homework.